In this lecture, we learn about eigenvalue and eigenvector. What is eigenvalue and what is eigenvector? Let T be a linear transformation from V to V. Let X be a non-zero vector and X belongs to V, and lambda be any scalar. Then X is called eigenvector and lambda is called eigenvalue if T of X that equals to lambda X, this is satisfied. If this satisfies, then X is called eigenvector and lambda is called eigenvalue, where X is non-zero. Also, lambda is called characteristics value or latent root or proper value. So eigenvalue is also called characteristics value, latent root, proper value, and X is also called eigenvector, characteristics vector if V is finite dimensional vector space, that is dimension of V that equals to n. Then T with a suitable basis alpha can be written as a matrix A, n cross n matrix. Okay. If V is finite dimensional, then T can be written as a matrix representation, and Tx equals to lambda x, that implies Ax equals to lambda x, that implies A minus lambda I into x that equals to 0 vector. That implies this is the system of homogeneous linear equation. That implies system of homogeneous linear equation. And since X not equals to 0, so non-zero solution, that implies determinant of A minus lambda I that equals to 0. If since X not equals to 0, since X is non-zero solutions of this linear equation, linear homogeneous equation, it is only possible if determinant of this matrix equals to 0. That implies A minus lambda I, this matrix is singular matrix. Okay. So if finite dimensional, then this happened. This is matrix representation and T is equals to lambda x, and since this is a matrix representation E, that implies A is equals to lambda x and A minus lambda into x equals to 0. This is the system of homogeneous linear equations, and since x not equals to 0 be non-zero solution of this homogeneous system linear equations, it is only possible if determinant is 0. Okay, and this determinant 0 implies A minus lambda is singular matrix, A minus lambda I that equals to 0. This implies the characteristic equation. Now, what is the geometrical meaning of eigenvalue and eigenvector? Since T of X equals to lambda x, then and applying T, we have Tx, there is a multiply of lambda x. Then if this, that means either applying this T of X, if lambda greater than 1, then X goes to Tx. if lambda equals to 1 and this value x equals to tx, that is this tx. If lambda equals to 0, then this is tx, this tx. If lambda less than 0, then this tx. That is, if x is eigenvector and lambda is eigenvalue, then always either translation or contraction. Okay, so the geometrical meaning of eigenvalue and eigenvector be, if eigenvalue exists, that is if eigenvalue exists, then t can translate or contract the vector x, either x contraction or translator. Okay, but no rotation. That is, if rotation can occur by linear transformation t, then eigenvalue does not exist. That is, if t rotate the vector x not equal to 0, then t has no eigenvalue. Example, let the problem be t maps r square square t of x equals to minus or x, and this is the matrix. Let t of x or minus or x, that means 1 and 0 vector goes to this 1 comma 0, and 1 comma 0 goes to t of 1 comma 0, that equals to 0 comma 1, that means this vector. So this vector goes to this vector, and 0 comma 1, this is 0 comma 1, and this is 0 comma 1 goes to minus 1 comma 0. So this vector goes to this. So this is the rotation, pure rotation. By geometrical view, we say that t has no eigenvalue or eigenvector. Let's see. A minus lambda I, that equals to minus lambda minus 1 minus lambda. Determinant of minus lambda minus 1 minus lambda, that equals to 0, implies lambda square plus 1, that equals to 0. And since this is the real number or real field, so this is not factorizable. Therefore lambda t or a has no eigenvalue. Okay, since t rotate the vector, from r square to r square by this linear transformation, so t has no eigenvalue. In a real field, t has no eigenvalue if t rotate the vector. So only translation or contraction of the mapping can only give the eigenvalue. Example, t maps r square to r square, t of a1 a2, that equals to a1 minus a2. And also this 1 comma 0, t of 0 comma 1, that equals to 0 comma minus 1. So this 0 comma 1, this vector, and this only goes to 0 comma minus 1. So only translate this vector. T is alpha, that equals to a, that equals to 1 0 0 minus 1. A minus lambda I that equals to 0 implies 1 minus lambda 0 0 minus 1 minus lambda that equals to 0. That implies 1 minus lambda into minus 1 minus lambda that equals to 0. That lambda equals to 1 and lambda equals to minus 1. So 1 or minus 1 are the eigenvalue. If you like my video, please share it and subscribe my channel. Thank you.